Okay, welcome everybody to this colloquium by Andrew Wray. It's a pleasure to introduce him. He's been an assistant professor at NYU since 2014. He got his PhD at Princeton University in 2010, working with Zahid Hassan, doing some of the first angle-resolved photoemissions on materials called topological insulators, and in fact showing that they had very unusual surface electronic states. He then did a postdoc at the Advanced Light Source at Lawrence Berkeley National Lab, where he developed techniques for resonant inelastic X-ray scattering. Again, a X-ray technique that allows probing electronic structure on a very fine and with temporal resolution. He did a year at Stanford at SLAC before coming to NYU, and he's well known for developing X-ray spectroscopies that can provide insight into what are called correlated materials, materials in which the electrons correlations are important. Think magnets or superconductors and things like that. So he's going to tell us about things he's been working on in the last several years at NYU and insights he's gotten into materials in 6 dimensions. Take it over, Andrew.
Thank you, Andy. So that was not the right button. Let's see, I'll click on this and now, yes, it advanced. So it's exciting to be speaking on the anniversary of the WHO declaration that we're in a pandemic. It was also a year ago today that we began all remote instruction. And if you really want to relive some of the anxiety of the day before, we'd had the famous words from our then president, and it will go away, just stay calm, and it will go away. And Churchill could not have said it better. So at the time, I was preparing to give a colloquium on March 26th, 2000. And that was, I'm going to show a slide that I put together for that colloquium. It's somewhat dated, but it explains to some extent why I did not give the talk then. It was just a very intense period. These were some people that live with me this was taken on the new year. We have a tradition of making a tower. My daughter Skylar and Oscar was a super cute 1-year-old. And I tried creating a chart of what things were like sort of day to day. Stress has units of Pascal, we know that, but you may not realize that Pascal was, his father was a single parent who homeschooled him and obviously did a very good job with Blaise Pascal. So Pascal is an excellent unit, not just for stress, but I would say for hope and for tears as well. So, and Massimo at the time had made a comment that 5 minutes is the new infinity because things were, so we have our units, and shortly into it, we all redesigned our classes, which was involved some Pascals, creating data analysis projects with some help from the department. And then weekend childcare, my daughter's Japanese weekend school and so on ended. And then school ended, which was kind of nice at first, actually. The stress didn't mount right away, but then you sort of realize what you have to cope with. And then you remember that you like your kids and there are wonderful experiences there. Anyway, and that takes us through many infinities onto the present day. So, oh yes, there was a little blip when we realized that when we were told by our school that remote learning meant a 10-minute Zoom call every day. That was not, that was unfortunate, but the fall was better than that anyway. So we are back to physics, which is a much better place to be than the previous slide. These are the people who performed most of the measurements and analysis that you'll see in the next 40 minutes or so. And these people did, I suppose, a lot of it too. So I guess Erica's work, Erica Cotta in my group, her work will be highlighted in particular. Lin isn't actually with us anymore. He's faculty at Southeast University in China and setting up his own group. And Yishuai is about to leave for UPenn for a postdoc. We have also had a couple of master's students from the DS3 program and in the Center for Data Science, and they've been extremely helpful in some of the deeper data analysis that we're getting into. This slide is going to get about 60 seconds, so don't feel that you have to parse any of it out. I just wanted to start by saying that what we do as a spectroscopy group is basically to take pictures of what electrons are doing inside materials. And these are some of the representations that are that relate to things that will come up in this talk in particular. All of these are from are relatively recent, or all or most. Since I'm speaking to my own department, it's a good time to give a shout out to all the people that have been in our group over the years. Howie, my student who graduated a year ago, several students that have done master's degrees with us who are now all in very nice PhD programs. And we've had a whole bunch of undergrads and even a couple of high school students. I'm just highlighting a few undergrads that are Edwin and Rongjie are first authors on papers with us, and Janet contributed a huge chunk of to something that we did. Anyway, there are many people to be grateful to. The science that I'll be talking about is rooted in a major trend for spectroscopy now, that we are entering what's called the ultimate generation for synchrotron storage rings, which is making it possible to perform spectroscopies, very powerful spectroscopies for imaging electrons in materials in a way where you're not just seeing your entire 1 millimeter by 1 millimeter sample surface, you're zooming in on maybe 100 nanometer regions and doing microscopy and spectroscopy at the same time. So they call it spectromicroscopy. I will unpack that later, but this generational upgrade in the technology is what's making it possible. So as the talk moves along, I'll talk about what that means for some specific quantum materials like topological insulators and things that we've done, and some of the profound opportunities that are going to open up as these technologies become mature over the next decade or so. At NYU, we're very fortunate to be close to the National Synchrotron Light Source 2, which I need to find a good way to say that. It's a bit of a mouthful. NSLS2 is one of the 3 major synchrotrons in the US, and it's the only one that you can say is sort of an entirely new facility right now. We use this quite a bit for our research. We also have a very nice in-house ARPES system that doesn't allow us to do spectromicroscopy, but it's a real workhorse for certain kinds of characterization. And right now, like I said, sort of we're entering a new generation for the technology. New synchrotron light sources are cropping up all over the world. All of the major US light sources are currently, including NSLS2, are currently undergoing major upgrades in line with the new technological paradigm. And there's been a lot of development of synchrotron light sources in China and Europe over the last decade or two. In China, it feels kind of more profound to me because although they're having trouble getting beamline scientists to create them, I did research there a couple of decades ago, and there was almost no cutting edge physics. And now the face of the country has really changed in that regard. So when I say the ultimate generation, the synchrotrons have gone through several generations. What a synchrotron is at heart, it's a particle accelerator. It takes, at the advanced light source, a 3rd generation synchrotron in California. that I used to work at, you have electrons orbiting in a storage ring where the same electron will go round and round for hours before scattering off something. And they travel at, I believe it's 99.6 more nines and then a 6% of the speed of light. And they pass through magnet configurations that are called undulators that cause very bright synchrotron radiation to come out that's used in experimental beamlines, experimental end stations where we perform the actual experiments. It sounds a little bit funny to be doing a lot of science at a glorified X-ray machine, but one has to remember that there's really a qualitative difference between an X-ray tube and what you need to use X-rays to study materials, what you need to image the finest structure of electrons. The small wavelengths of X-rays let you get at the smallest scale quantum structure of what electrons do inside materials, but you need a brightness that is, this is a log scale on the left for brightness, that is about 10 to the, let's say, call it 11 orders of magnitude brighter than what you have coming from an X-ray tube if you want to perform cutting edge spectroscopies. The ultimate generation is just an upgrade to the focusing optics for the beam that goes, the electron beam in the synchrotron that makes the light coming out much more coherent, so it interacts with optics better, so you can focus it much better. Actually, when they rolled out the previous generation of synchrotrons around 1990, they already, in designing that, they realized that their focus was bad, that the focus of the beam needed to get better by a factor of 100 or so to get optimal performance. But it took over a decade to overcome the technical hurdles to making that a reality. And then designing new facilities and so on took time, which is what brings us to the present day. If I were feeling just a little bit more awake, I would say something about the ultimate generation of synchrotrons not being the generation that lived through the Depression and fought in World War II. But okay, so what it means to take a technique like angle resolved photoemission, which I'll explain to you in a little bit, to take a powerful measurement technique from something that's looking at the entire surface of a sample, that's looking at half a millimeter region, something like this entire image, to looking at 100 nanometers, is not very intuitive. When you zoom in on a tiny piece of sample, what you tend to find is that there's a lot of complexity there. If you took, this is a sample of UTE2 that I'll show you, it's an exotic superconductor that I'll show some data on later. If you took every atom at the surface and blew it up to the size of a grain of sand, you would blow our average sample surface up to about the size of Manhattan. And the complexity that you see in this optical image, the different kind of cleavage regions, it's invisible here, but a tiny gradient in the stoichiometry of the sample and the chemistry of the sample as you go across, as you move across it. The various properties of these different surface regions give you a lot of the complexity that you'll have in different neighborhoods on the image on the right. It's but one needs new data analysis paradigms if you want to make use of that kind of higher dimensional spatially resolved data as well. So there's a lot to process with this kind of upgrade to the technique. As I approach this technique, a lot of, and much of the field approaches it, a lot of what motivates us is another relatively recent discovery, the discovery of topologically ordered materials. This relates to the 2016 Nobel Prize in Physics, which was about addressed sort of early discoveries of topology, such as for the quantum Hall effect, how you can have something that if you have a material that's an insulator in the bulk, but that has some sort of exotic quantum topology, you get emergent edge states that are that live in the fragile environment at the surface or edge of the sample. A lot of the materials people are interested in today have so-called topological order of one sort or another, and that manifests by and large again in surface states that respond, that have a different manifestation depending on the local environment that you have in different regions of a sample surface. So if you want to get their intrinsic properties, you really want to be able to zoom in on a local region. And this technique of spectromicroscopy is kind of a precondition for that. There isn't, so for what we call 3D topological insulators, a topological insulator that can be a topological material that can be just a rock that you hold in your hand. There's not a very long history. The original prediction of the state of matter was back in 2005, and I was involved in the discovery of some of the first examples of it with the Hassan group. There are many other kinds of topological order, like topological superconductivity, topological crystalline insulators that I've been involved in exploring over the years. But this talk won't go very extensively into that. I do want to give a quick example of what it means for a material to be a topological insulator, because that is the scenario that I'll focus on most. Bulk materials can be typically either conductors or insulators. If you have electronic states at the Fermi level, which means you have some state, which means that you have, you fill up all of the electronic states up to a certain point, and then there are more electronic states immediately above that. Then you have a metal with just putting in a little bit of energy, you can create excitations that will be involved in carrying a current. If you have an insulator, so this is energy on this axis in this figure and momentum on this axis, and we have shaded in a continuum of bulk states, and there's a gap in the states. You have to ignore this zigzag, and then you have more states up here. If you fill up all of the states beneath this gap, you have, then what you have is an insulator. You have a big energy gap if you want to excite an electron from this lowest occupied state to these unoccupied states and get it moving. It was previously thought that if you had states at the surface of an insulator, they had to, they would look like this in momentum space. They would sort of connect with one another. They would form their own pockets in energy, and you could have gaps between them. In a topological insulator, what you have is states that zigzag their way across the bulk band gap, and that are like a string that connects between the states at the top and the states at the bottom, so that you cannot remove these surface states. If you try to pull them down, you'll just pull more of the string from the state continuum on top. So this gives you, these states also have exotic properties in terms of their the spins of the electrons. They constitute a new kind of electron system at the surface of a material. This is, I realize this is kind of hand wavy, but I just want to walk through a very basic picture of what we're grabbing onto in studying topological materials. So back in 2011, I was involved in work where we actually doped a material from a trivial state to a topological insulator state. On the left, this is the composition. We're doping in selenium to turn it into a topological insulator. You have energy is on this vertical axis. You have the conduction states on top and the valence electronic states on the bottom. And the energy gap here is the insulating energy gap. And as we dope, the insulating energy gap closes. It opens again. We don't see the states on top anymore, but we have this crisscross. These are the surface states that I was talking about. For when we created this paper, I did a little quick model of it. This is an image of its momentum on the in-plane axes and energy on the vertical axis. You have bulk states that are sort of shaded in at top and bottom, and surface states that cross from the bottom continuum of bulk states to the top continuum. And this is taking the simulation from a trivial regime to the non-trivial regime where you have topological surface states. To the right, this is a picture of a sphere turning into a donut. I realize that's not very inspiring. It is just the classic image that people show alongside topological electronic order, because this is a donut, is in a different topological class than a sphere, due to having a hole in it. You can no longer deform it to turn it into a sphere. So what you've really done when you've created this inversion is to swap symmetries, where originally you had a positive parity symmetry for these bulk states on top and a negative parity symmetry on the bottom, and you've swapped that. So it's plus on the bottom and minus on the top. Anyway, getting into practicalities. When we study a material, like bismuth selenide is a classic topological insulator that looks with an electronic structure that looks like what I was just showing. What we do is we take a chunk of the material and put it into ultra high vacuum, and then we knock off the surface of the material. So we get we knock off a piece of the top of the material. So we get a new surface that's cleaved, that has never seen air, that's ideally perfectly clean. And the surface electrons tend to live in the top layer or so, and bulk electrons are sort of everywhere. Then we shine light on it and knock electrons out and measure the energies of the electrons, energies and momenta of the electrons outside to reconstruct the energy states they were inside the material. If we use a very low photon energy or an extremely high one, we can see the bulk states pretty well. This is a measurement like that, where you see these are bulk states. They look like a parabola, because we're used to thinking of, for a massive particle, energy is proportional to momentum squared, as p squared over 2m. So energy on this axis, momentum on this axis, and the states are a parabola. Great. Then, but crossing from the top of the image to the bottom, we have this X that does not look like a parabola. It looks like a set of massless states. That's what the surface state looks like. If we use another energy that, which is actually more common for ARPES, that only gives us sensitivity to the surface, we stop seeing the nice parabola for the bulk states. It sort of fills in. We're no longer resolving the momentum of the bulk states, the z-axis momentum of the bulk states, the surface normal momentum. But we see the X perhaps more cleanly. We don't, we get this, I realize the contrast of the image doesn't make it very obvious, but we get a nice X shape for the surface state. And this is a common feature of the investigation of topological insulators, by the way, because the surface state sort of blocks the surface, bulk electrons have to tunnel through it. We don't tend to see clean momenta, z-axis momentum for the bulk states. Bulk states tend to look like shaded in continua. This is a measurement on bismuth telluride. So we see a clean surface state that looks a bit like an X, and then this shaded in blob for the bulk states. So, by the way, please don't hesitate to step in with questions while we go through. I know it's harder with Zoom, but I'll probably touch on a relative diversity of topics. So if it helps to pause for a moment, please go ahead and stop me. Now, we first conducted a measurement, a spectromicroscopic measurement on bismuth selenide, on that particular material, I think in 2017. And we learned something that did not make us happy. Actually, while I was playing with this slide, the best units or most exciting units I found to address it are gigatons of TNT. As you focus a synchrotron beam more tightly, you're coming in with very high energy photons. They're being absorbed in the top nanometers of a crystal. And on average, if you just count the energy deposited in those atoms that are directly absorbing the photons, it is the energy density that you're delivering is equivalent to 1 gigaton of TNT per meter cubed, per second, is the missing unit. Now, you can also conceptualize that as for a 10 micron spot, which is the most common form of spectromicroscopy today, that's each atom at the surface is absorbing 1 photon per second. As you try to move down to the limit of what you can do before you start heating your sample too much and creating other problems for the spectroscopy, you start shining about close to 1 million photons per second on each atom, or being absorbed per atom on the surface. And that can be fine. If you're studying graphene, something with very strong covalent bonding, even though you're dropping 100 EV per photon, the efficiency with which that breaks bonds is very low, and you will probably not change the chemistry on the time scale of your measurement. But for many materials, you can see aging even if your beam spot is 100 microns or 500 microns. And for those materials, one has to start considering this. For topological insulators, where the surface state lives in that sensitive, where you're studying something that lives in the most sensitive region of the sample, and the surface where atoms can be knocked out into the vacuum or can react with things in the vacuum, it's a particular concern. So we saw that this is the Dirac cone of bismuth selenide. We saw it shift in energy with time as we let the beam spot dwell. And since I'm calling it the dark side of spectromicroscopy and comparing it with energies that could destroy the world if we scaled them up to our power energy densities that could destroy the world if we scaled them up to the meter cubed scale, we may as well show the Death Star. Now, so a focus of our group over the last few years has been to see, so it's great that spectromicroscopy works very well on some materials, on a certain fraction of materials. But if you want to extend it to materials with more ionic bonds, like more often to oxides, to a broader range of topological insulators, we need to have a new way of conducting the measurement. So, Erica has been the key driver in our group of a new kind of approach, where rather than measuring for a long time at single spots on a sample surface, we take the beam and measure a grid of points on a sample surface with, in this case, about a 10 micron step between the points. This is not the entire grid. It was in all about 1,000 points for this particular measurement. At each point, we get sparse data. This is the data set that we got from one particular, this is an image with momentum on this axis and energy on this axis that we got from one particular spot on a sample surface. This was as much data as we could get before that spot was going to age and the energetics would change. So that seems bad when you're used to analyzing single images, but one can recover a beautiful image if you just average over the surface. Ta-da, we have our nice Dirac cone. And what Erica found was that you can actually recover a great deal of information from these single images if we take templates from the original image. So here she's extracting a template from this momentum energy region and seeing its cross correlation, which is a kind of slightly corrected inner product with this sparse image. And you find with momentum on this axis and energy on this axis, the cross-correlated template locks on at a certain point. You get the energy of the Dirac point, and you get how you need to shift this image left and right to find that Dirac point too, which tells you the local orientation of the surface. Immediately, this gives you, knowing the momentum axis onset gives you the curvature of the surface. And if you apply a correction to each image for that curvature and redo the sum, you go from having a blurry image that's average, that's equivalent to a conventional measurement, to having a far sharper image that makes use of the entire data set, but that's corrected for the roughness of the cleavage of your sample. Now, I'm not even going to show that because although that's interesting, it's not very profound. Where things get more fun is that you don't just get corrections that let you realign images from different parts of the sample surface. You also find that the energies of features that you find in different parts of the sample surface are different. This is a map of the energetics of the Dirac point of the surface of the topological surface state as you move around. In some regions, it's shallower. It's closer to the Dirac point is closer to the Fermi level. It's as if you're hole doped. In other regions, you have these chunks where it's deeper, where it's like you're more electron doped. Now, the bulk states, the bulk electrons can also be tracked, and they have some correlations with this. You can see the bulk states look hole doped here where the surface state looks hole doped, like there are fewer electrons there. But the correlations are not perfect. And therein, you gain potentially the power to take partial derivatives on your electronic structure. You've gone from having a single measurement to having sort of a cloud of measurements that you can either frame as a doping series, or you can frame as sort of a traditional doping series, or you can take in new directions as maybe a multi-dimensional, some sort of multi-dimensional doping series. Now, I say that because I want to scare you. Anytime you start doing something very complex with a data set, you open the door to artifacts of the analysis, or to it just taking a long time to figure out what you've got. We approached this, fortunately, with a large collaboration that included some very strong STM experts who had characterized defects and what things, how you can know the chemistry of this particular sample, bismuth selenide, from atomically resolving real space images. So we were able to tell not just what things looked like, not just that there was sort of there were doping gradients in a range of environments, but we could see that made sense based on the range of stoichiometries that you find as you move to spots that are on the order of hundreds of microns away from one another on the sample. That's the case for another material that I'll give an example of in just a moment, samarium hexaboride. So what we did with this in the case of bismuth selenide was we created what we call binning series representations, where here we're having the bulk states, we're binning the data in the order of the bulk state energies. So having the bulk states come down in energy. Here's a profile just in the center of the image at zero momentum. And you can see that the leading edge of the bulk states is moving down as you go across this series. And there's some correlation with what the Dirac point of the surface state is doing, but it's not that strong. It varies as you go through the series. We did the same thing with moving the Dirac point independently of the bulk bands. And what we found was that surface state parts of the surface state that are close to the bulk states move by a lot when the bulk band goes down. Like the Dirac point is close to the valence band here, and this upper branch of the surface state is close to the conduction band. These move down by a lot. States in the middle of the gap don't move by much as you shift the bulk band. That corresponds to what you expect in a tight binding simulation. Simulation has been adjusted to set the motion of the surface state to 0 in the center of the band. It's somewhat arbitrary, the difference between how much the Dirac point and the rest of the band moves in the simulation versus how much the middle of the band moves has an arbitrary offset parameter to it. As you move the Dirac point down, we can eventually push it into this valence band, at which point we expect the energy of the surface state to have sort of a little bit of a rebound relative, the surface state feature to have a Dirac point feature to have a rebound relative to the bulk states. And we see that in the data. At first, we thought this was represented a mistake or something fundamentally unreliable in the data. So we were very happy to find that it's a natural sort of feature in a tight binding model, in a very simple model for having somewhat independent energetics of the surface versus the bulk of the material. So let's see. Taking this further, where this, I would say, gets even more interesting is when you have many body coherence in the mix, where you have strong interactions between electrons that can drive other kinds of many body order, or that can fundamentally interfere with the coherence on which the topology is defined, and the coherence that gives you the surface state and gives you a clear sort of this is getting into technical jargon, but gives you a clear quasi-particle picture for the low energy electrons. A topological insulator material that lets you play with that is samarium hexaboride. It's strongly correlated, and you only have some incoherent F orbital derived states at the Fermi level associated with samarium that only gain coherence and start to look really like quasi-particles as you go to very low temperature. When they do, you have a topological gap that is going to be crossed by surface states. So we were in the middle of an investigation of these materials anyway, that what happens when you alloy them, when you adjust the chemistry, which there's a PRL that was just accepted that I won't delve into due to time constraints. But what we found when we took these topological insulator, these strongly correlated topological insulator alloys and applied the same technique to them very recently, is that there's potentially a lot more richness to what you can find. You can look at the width of the F electron states, which tells you sort of how coherent the states are. When the F electronic states are broader, or it means that you're starting to depart from the quasi-particle picture that gives rise to band topology. And when we dope the material heavily with a magnetic element like cerium, we find that we can get those widths to be very, we can suppress this coherence almost to the point, in this case, where we're losing the surface state. So we can play with that physics as a departure from the topological regime. You also get a gradient in the sample that represents chemical doping, where you have more electrons on this side, fewer electrons on this side. The cleavage termination can be identified from a so-called multiplet feature in the spectrum. The surface tilt can again be identified. And the intensity of surface states has an interesting correlation with all of this. You'll see where the coherence states becomes very poor, where the F states are very broad here. You actually, we're not, it's in this case, let me pause on that because this is, yeah, no, where this is, where the coherence is, where the states are narrow, you get strong surface states. Where the states are broader, you get some suppression. Anyway, it opens the door to investigating a wide range of correlations.
Can I ask a quick question, Andrew?
Yes.
Does the europium go in and cerium, are they uniform in the material? Should we assume that they're just disordered but uniformly distributed on the cerium sites?
Yeah, from STM, for example, we can spot where the europium atoms are. There's a characteristic blemish, and this is for 20% europium doped. You can't see it. This is tagging all of the europium atoms, and this is looking at comparing sort of with a Poisson distribution, the chance of finding different numbers of them in different bins. They're fairly uniformly distributed from what we can tell.
Thank you.
Yeah, there are elements of this analysis. The fit of F bandwidth actually breaks down in this corner, so one shouldn't take some of the correlations very seriously. I'm kind of sweeping through very new data in this regard. In the case of samarium hexaboride, again, a fun thing for us is that we can dope the material. Because of the complexity of the surface of this material, there were no previous doping dependent studies, and we're able to separate out the density of samarium versus boron at the surface on this vertical axis versus the amount of electron doping that you have on the horizontal axis. And what we find is that regardless of the surface, you get a very similar trend as you add electrons, the Fermi momentum of the surface state grows, which is what you expect for doping. So we can get the first clean doping series to exist on this material, while simultaneously getting a richer understanding of what you have simply from having a complex polar surface. Something fun about that in turn is when you have strong correlations in a material. When I say strong correlations, I mean that electrons, there's a large energy cost to squeezing electrons on top of one another, to having a large density of electrons. Strong correlations are one of the pillars of the quantum material community. When you have effectively very strong correlations in a material, it can give you, as you change the density of electrons doped into a material, it gives rise to a lot of different kinds of configurational states and instabilities that can support high temperature superconductivity or a range of other emergent phenomena, magnetism, and that, so to be able to investigate a strongly correlated system, the electronic structure of it, you really want to be able to dope it. You want to have this particular axis to get at the heart of that kind of physics. In this case, a very quick thing that you can find is there are these spectator d electron bands of samarium that are not very strongly correlated. As you dope the F electrons, as you shift the chemical potential of as you shift the binding energy of the F bands by just a few MeV, just on the scale of 10 MeV, you find that the D bands shift by, these are measurements for different surface terminations. The D bands shift on the order of 100, 150 MeV. That's exactly what you expect, because the F electrons are the ones that are strongly correlated. They're the ones that don't want to be squeezed on top of one another. So as you try to pull the F band down in energy, what you're effectively doing, you're squeezing some electrons into the F band, but you're squeezing a lot more into the D bands, because the F band is effectively is resisting taking on more electrons. And what that looks like in our data is that the D bands pull further beneath the Fermi level. In fact, we took a tight binding model from the literature and threw in a Hubbard U term. You set it to 2 eV on site, you get something that sort of matches the data. 4 eV maybe it's a better average match for what we see. So we can clearly see the strongly correlated nature of the SMB6 electrons, which is again something that at this sort of fundamental quasi-particle level, people had never been able to really get into. Where I would really like to be able to go with this is, again, sticking with the idea that we want to be able to play with topology, but also potentially strong correlations and coherence. We want these as our, let's say, 3 pillars for realizing exotic quantum states of matter. It would be very interesting, instead of looking at coherence in a topological insulator gap and the corresponding surface states, to look at coherence in what's called a topological superconducting gap. Topological superconductors are materials that can realize exotic Majorana-fermion states on the surface. Many of you will have heard about them and maybe thought deeply about them. And for those that haven't, I won't really delve into them. But superconductivity in general has a much smaller energy gap and is, in conjunction with strong correlations, can be very difficult to understand, but is potentially very technologically important. So reaching down to the sort of resolution scale that you need to understand that, and parsing out these topological surface properties in the context of that sort of material is going to be a frontier that I think we'll get to with some advanced end stations. The resolution for ARPES in principle can get down to, this is very much in principle, can get down to like the scale of 50 micro eV. More practically, you're talking 1 MeV or so. It's much easier to build a beamline around that sort of spec. My group has been interested in this particular material, uranium ditelluride, which is seems to be the first topological superconductor to be an analog of superfluid helium-3. It's the thought of seems to be the solid state analog of that. It was discovered by collaborators of ours at the University of Maryland in 2019. And they're the ones that created this image with Vikings in it, which I found too cute to resist. But we conducted an initial study on it using ARPES a year and a half ago, and that came out last year, in which we found that the electrons in it are quasi one-dimensional. So we were just taking a picture of the energy versus momentum contours of the electrons, and we found that the states only have velocity in one direction, but they're quasi one-dimensional in 2 different directions. Sorry, I'm juggling the picture of all of you so that it doesn't block my view of the things in the slide. It seems like the mouse is dancing around. There are chain structures in the material. Tellurium atoms have a chain along this y-axis. Uranium atoms have a chain along this x-axis. So uranium electrons, due to the orbitals that they occupy, can basically only move in this direction, and tellurium atoms can only move in this direction. That was the result of this study. There are also epsilon electronics. These are relatively weakly correlated electronic states that are one-dimensional. There are also some more strongly correlated states that are higher dimensional that I won't show, but that have a strong interplay with one of these bands, which we speculate is what is responsible for the superconductivity. If we really wanted to zoom in further, this study was performed with a 100 micron beam spot, and you can see what that looks like on the sample. Well, 50 to 100 microns. If one wanted to zoom in and have something truly homogeneous that's not going to so that the quasiparticles aren't going to look so broad, so you can get a clear look at perhaps the topological surface states in the superconducting regime. You would need to go significantly smaller. So just to make it more concrete, the kind of challenge that one is facing at a technical level if you do this. A beamline these specs are planned for beamlines. I will not talk about that right now unless there are questions, because I do not know if the beamlines will make their specs, and sometimes sometimes certain details like that may be internal at this stage. So another thing we'd like to do is at topological insulator surfaces, you can have, if you have complex nanostructure, my group has been part of showing that you can have other kinds of emergent states that are sort of, that emerge from the exotic topological surface electrons. This is an image of the surface of bismuth selenide that's been MBE grown. You see a lot of terraces, and at the edges of these terraces, STM shows us that there are in-gap states, the nature of which has never been seen with a quasi-particle resolving probe. We had a paper a couple of years ago in which we explored these for the edge state scenario, and found that that generically you expect the in-gap states to also have a weird topological character where they're quasi one-dimensional states that are spin polarized and that have a momentum energy dispersion that connects to the Dirac point of the material. And so you can imagine them as, if you put a chemical potential near this Dirac point, these edge states will carry electrons with one spin in one direction and with the other spin in the opposite direction. They potentially can be an interesting kind of nanoscale wire that's, so if we could zoom in on regions that have dense steps, or if the beam spot were down to 20 nanometers, so we had enough of a signal from one step, we could kind of generically resolve emergent electronic structure features from nanostructure like this. So that's, I think if I give you anything more, it will be absolutely too much. So I will leave with this summary. Again, spectromicroscopy is bringing on great opportunities, but those opportunities are way outside the roadmap of what we envisioned studying a decade ago. They relate to nanostructure. They relate to big data analysis of data sets that are 1,000 to 100,000 times as large as the data sets that we were dealing with a decade ago. And delving into that is a lot of fun. It's something that we're in a position to do right now with the earliest realizations of this. And I have my vision of where I think it's going to go, but I am excited to see what it will actually be like. So let me leave it.
Yeah, thank you, Andrew. Thank you for that very interesting talk. Please use the chat or just jump in if you have questions.
Yeah, so I have like a very basic question, and you're just gonna have to excuse my dog, who's gonna bark a few times. So I mean, this is so basic, but you are studying all of these, all of these materials, and I guess but it seems like it's a variety of materials. It's with a variety of motivations, and I'm just wondering, like, how do you choose, like, what drives your sort of decision on, well, I'm really interested in the surface states of this material versus that one? Like, can you like, are there practical things you have to worry about, or are there, you know, very specific science questions that you worry about, or are there standard materials that sort of people want to understand more? Like, can you just talk a little bit about that generally?
Yeah, so to some extent, it's we have certain sample growth collaborators that we work with closely, and every so often they bring me something fun, and I sort of I assess that with respect to our fundamental science priorities. And with respect to these particular, the data that we're mostly focused on here, bismuth selenide is a model material for topological order. It has one of the nicest looking Dirac cone surface states, and it's extremely easy to study nicely. So for exploring what you can do with a new technique, it's a great way to go. SMB6 was always number 2 on our list for spectromicroscopy because it's not a model material, but it's a material where non-spectromicroscopic studies are really bottlenecked by the complexity of the surface. And there are great features for spectromicroscopy to latch onto in the kind of analysis that we can automate. So UTE2 is not an immediate candidate for spectromicroscopy. We went with UTE2 because just generally because we like topological materials and it was hot, and not as in hot radioactively. It's actually about as radioactive as one of our samples is, about as radioactive as a banana, but it presents a very enticing low energy topological picture that we wanted to dive into.
Thanks.
I think I see Glennis, but I don't know if I see everybody. Go ahead, Glennis.
Thanks a lot. And thanks for surviving to tell us the story. I had 2 questions which are probably coupled. One was, most of the stress was on analysis. And I'm just curious, as an experimentalist in this field, does the laboratory provide the detectors to a large extent, and your main work is in the analysis, or you just decided to tell us about that because it might be more accessible to us? And so the first question is, what's the sort of real experimental side of it like? And then a second related question is, how much competition is there worldwide? Are there other people who are racing to do the same materials and just at different laboratories? Or do you, for some reason, have special apparatus that nobody else has? Or how does that all work?
So being closely coupled to NSLS2 is a huge, is a big deal for our research program. Like I said before, there are 3 major synchrotrons in the US that are that have nice capabilities for spectrum microscopy. Synchrotrons are big operations that have annual budgets like on the order of $50–60 million. So they are, a lot of that goes into the development of the apparatus and even to infrastructure for some basic analysis, but they tend not to have but most of the scientific program is outsourced, and the development of the fundamental sort of algorithmic approaches that you need to make use of spectrum microscopy to date are largely also outsourced. That's sort of where we're coming in. We collaborate closely with beamline scientists, and there tend to be NSLS2 does have a big data infrastructure investment program going on right now that we are trying to provide tools to that will serve the rest of the community to make this sort of analysis more widely available. There's a big cost of entry to perform this kind of analysis, and traditional measurements that are not big data, where you just dwell on one single point on the surface with your tiny beam spot, do work very well for certain classes of materials. So what that means is that there are groups that can step right in and use it without having to overcome these algorithmic challenges. And that, so we are, where we're specifically pushing the envelope is in terms of trying to broaden the community base that can use this by enabling these new analysis paradigms. I'm not sure if that, it was a broad question and I kind of zeroed in on a couple of things.
That was helpful, thanks.
Can I ask something? Andrew, your title said about imaging in 6-dimensional space. I counted dimensions and I didn't count to 6. Can you explain the 6?
One of my favorite comic strips had a caveman comic about a week ago saying it was a caveman abstract mathematician who only worked with numbers 6 and up that had no application to the real world. Yes, to some extent, counting up to 6 is a little bit, the 6 dimensions would be 3 dimensions of momentum.
Okay.
One of energy.
That much I understand, yes.
And most of the time with surface states, we don't care about one of the momentum dimensions. So, but for SMB6, we do care about that. We care about studying the bulk states as well, because we're getting the first doping series on the bulk states. So, and we can study that dimension by varying the incident photon energy that we use. That changes the bulk z-axis momentum that you resonate with. In the case of, again, topological insulators make it harder to study that dimension, but not impossible. It depends on the specific region of energy and momentum space that you're looking at, exactly what you can resolve, or the exact measurement configuration.
So in the end, your 6 is 3 plus 3. It's 3 coordinates and 3 momentum.
And well, 3 plus 2 plus 1. 3 momentum, 2 real space, 1 energy.
Okay. But isn't the energy a function of momentum? So it's not independent.
No, so these images have momentum on this axis and energy on this axis. It's the binding energy of the electron. So we come with a photon and we get an electron out. And
oh, I see.
depending on the binding energy the electron originally had,
I see. Okay, so you have electron out. Yes,
yes.
That's what. Okay, thank you.
No, it's true. Otherwise, it would just be 1 energy, the photon energy, or
right. Yeah,
like in STM, you only have 1 energy.
Okay, thank you. I understand.
Any other questions? And maybe I'll jump in. Oh, Paul, go ahead. Unmute yourself if you want to ask, Paul.
Good idea. Okay, I just wondered about the triplet. What's the evidence for there being triplet superconductivity in the material?
There's a bunch of evidence. I may not be the best one to tell the full story, but so first of all, let's see how much of this, we have field on this axis, superconductivity on this axis in this phase diagram. This is, I believe this is angle that the field is applied along. Superconductivity persists way beyond the critical pair breaking field that should break Cooper pairs, cause them to prefer to become triplets.
So it's way above the Pauli limit, is what you're saying.
Yes, exactly.
And by how much, out of curiosity?
You
don't know.
Really
okay.
Not the one to tell this story because I've been focused on other projects since the last time I delved into the details. We do have fresh data on this material, but we're not but we're writing another paper before we write that paper. So I'm a little bit removed from it. You also, but no, there are several things in terms of the, let me see, the lack of a night shift as you go into superconductivity, it's theory that tells us that it would be topological superconductivity. That's not, there are experiments that hint at seeing surface states and so on, but it's not as concrete as one would want. The real, but it is, it's, no, there are other, the case for it being triplet-like is very robust.
Okay. Josephson tunneling?
Now let me, I don't remember.
Okay, I was just intrigued because there are lots of things that were claimed before and weren't.
Yeah, there are certain things, for example, the superconducting transition happens in 2 stages. You can have cases where you get a superconducting transition to and then at slightly lower temperature, you break the symmetry of the triplet up versus down. The symmetry is stabilized by spin orbit coupling, which tries to give you a superposition of the spin up triplet and the spin down triplet as a coherent superposition as the ground state. But when the superfluid density becomes high enough, you then get a magnetic transition within the superfluid. So that's observed. It has, it's
like helium, as you said, like helium-3.
Yes.
Maybe.
Yeah, no, I'm drawn to the exotic details rather than the nuts and bolts of it, simply because there hasn't been there hasn't been argument over the nuts and bolts. It's been seen as fairly decisive.
I see. Very good. Thanks.
Yeah, maybe I would like to continue on the vision on this nice slide. I mean, you said the energy resolution is getting better and better, so that you can hope to probe the triplet superconductivity. Don't you need a corresponding low temperature to get to the essentially to the limit where you're you're in the appropriate phase and you have the appropriate, you're not thermally broadened. Is that coming too?
So for temperature in this particular case, you would want, I believe it's, if you can't apply strain or do something special, you'd want about 1 Kelvin to have fairly good coherence, to be well up above the critical regime. And that
in the superconducting state, or
yeah,
okay.
Yeah, no, the superconducting state, the typical onset, if I'm not remembering incorrectly, is around 1.7 Kelvin. And new cryostats are such as one planned for a beamline I often use, are supposed to get you beneath 1 Kelvin on the sample. It's certainly been done before. There's, for example, the 1 qubit beamline at DESI. Is that DESI? Don't hold me to, I haven't performed a measurement there myself, that goes to 1 Kelvin, and there are in-house systems that go significantly lower. Yeah, it's seen as a priority now, and in contexts such as this. Historically, people have been fairly happy with 10 Kelvin, which is much easier to do. But
maybe if there are no more questions, I'll ask one more. You got me intrigued by the energy argument, that saying that you're getting all of this energy density into a very small scale. Where does the energy go? I mean, some of it goes into the photoelectron. Some of it, I assume, goes into just heating. What fractions are we talking?
So this, heating. It's kind of amazing, but you actually have time for phonons and electrons to carry the heat away until you get down to a beam spot of about 20 nanometers. And then you very quickly, as you try to push beneath that, you very quickly get to electronic temperatures of, let's say, 1,000 Kelvin. Or so this is where you would still get at 20 nanometers, you might not be getting 10 Kelvin electronic temperatures. There may be a compromise there, but you're still getting good quasi-particle coherence for most materials, thermal coherence. So it's, yeah.
So the vast majority goes into the lattice. Almost all the energy goes into the lattice.
Yeah, if you tell the story of it, you create all of the almost all of the photons are being absorbed in the top, let's call it 20 nanometers or less at these photon energies. And you get a primary electron that has order 50, 100 EV, and it quickly scatters with many other secondary electrons and shares the energy. So you get a downward cascade that is also simultaneously carrying the heat away. So locally it's very complicated. But empirically this has been characterized. The effective heat load has been characterized quite well. And I mean, it's basically, it's just an energy density, but other factors as far as whether or not you can perform a measurement include whether you're charging the sample and whether you're getting a space charge, which is too many electrons coming out at the same time in a small space, so they repel one another and ruin your resolution.
Thank you. Well, if there are no further questions, I think we'll end here. Thank you very much, Andrew, for this exciting tour. And I guess we have another talk next week. Okay, thanks again.